Have you ever looked at a transformer's nameplate and wondered what cryptic codes like YD1, 1, or DYN5 actually mean? Get it wrong, and connecting two transformers in parallel can cause a meltdown. Today, we're not just going to memorize those codes, we're going to understand them from the ground up, and we'll do it without a single complex equation. Our journey starts with something simple, a coil of wire. When current flows through it, it creates a magnetic field. This is Ampere's law. The current is the cause, and the magnetic field is the effect. The stronger the current, the stronger the field. And how do we know which end is north and which is south? Use your right hand. Curl your fingers in the direction of the current flowing through the coil, and your thumb will point to the North Pole. This is the right-hand rule. The end where the magnetic field lines exit is the North Pole. The end where they enter is the South Pole. Now, let's introduce a second identical coil. If I wind it in the same direction as the first and connect them in series, what happens? The current flows through both coils in the same sense. Their magnetic fields combine. We get a stronger, unified field. The North Poles are on the same side, the South Poles on the other. This is what we call additive polarity. The fields add together. Now, if we feed it alternating current, where the electricity constantly surges and collapses, the magnetic field does the same. It grows and collapses with the current. But watch what happens when I place these same two coils on a single iron core. Now I have a transformer. One coil will be my primary. I'll apply a voltage to it. The other coil is my secondary. It's just floating, waiting to do something. I apply an AC voltage to the primary. Current flows and a magnetic field builds up in the core. That changing magnetic field cuts through the secondary coil. And here's where Lenze's law comes in. Lenze's law says, the direction of an induced current is always such that it opposes the change that produced it. Mathematically, we write it as V equals minus N multiplied by d phi by dt. That little minus sign is the most important minus sign in electrical engineering. It tells us that the induced voltage is always in a direction to fight the change in magnetic flux. So what happens? When the magnetic field in the core is growing in one direction, the secondary coil tries to create a current that would produce a magnetic field in the opposite direction to slow down that growth. The result? The voltage induced in the secondary is the mirror image, 180 degrees out of phase with the voltage applied to the primary. To keep track of this relationship, engineers use the dot convention. We place a dot on the terminal of each winding that has the same instantaneous magnetic polarity. When the dotted terminal of the primary is positive, the dotted terminal of the secondary will also be positive, and vice versa. Now, remember when we placed the two identical coils, wound in the same direction, and connected them in series? We saw that their magnetic fields added, and we called that additive polarity. In that configuration, the dotted terminals were at opposite ends. If we reverse the winding direction of the secondary or swap its leads, then, by the same logic and explanation, the magnetic fields oppose each other. That's what we call subtractive polarity. You can easily test this at home with a small transformer and a multimeter. It's a simple experiment that proves these concepts. We'll just redraw these coils for simplicity and clarity. Based on our explanation, here's how you can determine the polarity of any transformer. First, apply a low voltage to one coil, that is, the primary. Then, connect one lead of the primary to one lead of the secondary. Now, measure the voltage across the remaining two leads. If the measured voltage is the difference, roughly the primary voltage minus the secondary voltage, then the connected leads are of the same polarity. This corresponds to subtractive polarity, that is, the dots are on the same end. If the measured voltage is the sum of the primary and secondary voltages, then the connected leads are of opposite polarity. This corresponds to additive polarity. The dots are at opposite ends. Now for the big leap. A three-phase transformer is essentially three of these single-phase units built on the same core. Their terminals are just waiting to be connected. And that's where our story gets interesting. If I gave you these three pairs of windings and told you to connect them, how many different ways could you do it? Taking into account the different winding connections, star or delta, and whether we reverse the polarity. Take a moment to think. We end up with 12 distinct practical and common ways of connection. We will see how to configure them in this video. These connection methods are what we call the transformer vector groups. Before we dive deeper, let's agree on some rules. Vector groups are written on nameplates as a code like DYIN1. The first, capital letter, refers to the high voltage winding connection. The small letter refers to the low voltage winding connection. And like in DYN1 means the neutral point of the star connection is brought out. The number following these letters tells you the phase shift between high voltage and low voltage, using the high voltage as the reference. Number 1 is like an hour on a clock. It represents 30 degrees. So 1 means 30 degrees, 2 means 60 degrees, and so on, up to 11 meaning 330 degrees, with 0 or 12 meaning 0 degrees. You may also see other letters like I, Z, or in some codes. Letter I means both ends of each phase winding are brought out separately isolated. Letter Z means a zigzag connection. Letter A means an auto-transformer connection. We won't cover those in this video, maybe in a future one. Here we'll focus on the most common and reliable methods. Now back to our coil's connections. Let's break them down. First, we can connect the high voltage windings in star, that is Y. That's the letter Y. And the low voltage windings also in star. That's a small y. But we have two options here. Remember our polarity lesson? If we connect them with the same polarity standard, that is the additive case, the voltage on the primary and the corresponding phase on the secondary will be in phase. That gives us a phase shift of 0 degrees, which we represent with the number 0 on the clock. So our first group is YY0. If we reverse the connections on one side, that is subtractive case, we get a 180-degree shift. On our clock, 180 degrees is represented by the number 6. So our second group is YY6. Next, let's connect the high voltage in delta, that is D, and the low voltage also in delta, that is small d. Again, two possibilities. First, we wind them in the same direction. Here, the voltages will be in phase. Now we have DD0. Second, we wind one in the opposite direction. Here, there is 180 degrees shift, and now we have DD6. Now things get really interesting. Let's connect the high voltage in star and the low voltage in delta. This combination is written as YD because a delta connection is made by connecting phases end to end. The voltage you measure on the output is not just a simple phase voltage anymore. It's a combination of two phases. This naturally creates a 30-degree shift between primary voltage and secondary voltage, even before we consider polarity. So with a YD transformer, star on the high voltage side, delta on the low voltage side, we actually have 4 common possibilities. Let's build them step by step. Start with the standard winding direction, that is additive polarity. The low voltage side lags the high voltage side by 30 degrees. That's position 1 on the clock. So our first possibility is YD01. Now, if we reverse the delta winding of the secondary, exactly like we did for the DD6 case, we add 180 degrees to that 30 degrees lag. 30 degrees plus 180 degrees is equal to 210 degrees, which is position 7 on the clock. So our second possibility is YD7. Keep in mind that we could also get YD7 by reversing the high voltage star winding connecting the coils with opposite polarity. However, to keep the high voltage side as our reference, we instead adjust the delta connection on the low voltage side. But if we instead reverse the connection sequence of the basic delta winding connection, which effectively flips the polarity of each coil, this mirrors the natural 30 degrees shift to the opposite direction. Now the low voltage side leads the high voltage side by 30 degrees, which is the same as a 330 degrees lag. That's position 11 on the clock, giving us our third possibility YD11. Finally, if we reverse the delta winding again on top of that YD11 configuration, just like we did before, we add another 180 degrees, bringing us to 330 degrees plus 180 degrees equals 510 degrees, which modulo 360 degrees is 150 degrees. That's position 5 on the clock, and it's our fourth possibility, YD5. The same logic applies when the high voltage side is delta and the low voltage side is star. That's a DY transformer. And honestly, this one might feel a bit clearer and more straightforward. We start with the base configuration, DY1, a 30 degrees lag. The low voltage lags the high voltage, which is position 1 on the clock. But if we reverse the star winding of the secondary only, we add 180 degrees to that 30 degrees lag, giving us 210 degrees. That points to position 7 on the clock, and that's our second DY possibility, DY7. Now, if we instead keep the star winding intact and reverse the connection sequence of the delta winding, effectively flipping the polarity of each delta coil, we mirror the 30 degrees lag across the 12 o'clock direction. This gives us a 30 degrees lead, which is the same as a 330 degrees lag, landing on position 11. That's our third configuration, DY11. And by the way, this is the most common vector group you'll find in power distribution transformers around the world. Finally, take that DY11 configuration, the one where the low voltage side leads by 30 degrees, and reverse the star winding again. As we've seen before, reversing the star adds 180 degrees. So 330 degrees plus 180 degrees equals 510 degrees, which is equivalent to 150 degrees. That's position 5 on the clock, and our final DY possibility, DY5. And these are the most common vector groups you'll ever come across in the field. So next time you see one of these codes, you'll know exactly what it means. And if you run into a different one, don't worry. It won't be too far off, and you'll be able to figure it out. If you found this video helpful, don't forget to like and subscribe. Thanks for watching, and I'll see you in the next one.